I want to start out by talking a little bit about whether we really need to explore parallel computing or distributed computing. The key question is do we need to have faster and faster computers or more and more computing power that we can throw at different problems? And I think the answer to that, and you might expect me to say this, is yeah, we do need more and more power. But let me just cite a few examples. One that comes to mind right away is the use of computing in meteorology or climate research. If you think about just an ordinary weather forecast for what's the weather going to be like here in Taylor in 2 days, the way that forecasting models work is essentially taking the atmosphere over some area of land, say the state of Indiana, and splitting it up into cubes that are certain width and height and depth. And for each of those cubes, trying to track the temperature and the air pressure and the wind speed and direction and the moisture and so forth, and then using that information, trying to apply various mathematical models that try to predict what's going to happen in each of those cubes over time. In order to get a more accurate forecast, or to get a forecast that takes into consideration more days with more accuracy, one important aspect of being able to do that is to reduce the size of the cubes. You'll reduce the level of error that's going to be inherent in that process by having finer grained data over what's actually taking place, say, over the state of Indiana. When you do that, however, you've now got more cubes in which you have to carry out these calculations, which means that we need to either have more computing power, or we have to deal with the fact that we aren't going to be able to forecast at all. If the computer is too slow and it produces forecasts in a longer period of time than the actual weather evolves, what we've got basically is weather verification and not weather forecasting, and that's not especially useful. And that's just one area where large-scale computing gets put to use, and there's a ton of others. So anything in computational chemistry, computational biology, protein folding, drug design, artificial intelligence research, machine learning, any kind of predictive modeling, processing images for things like games or films or educational purposes, modeling physical systems like the airflow over a wing for aircraft design or rocket design. In short, there's just no lack for problems that need more and more computing power, and there's no foreseeable end to that process in sight. So it's worth asking the question, however, whether we need to do parallel computing in order to be able to bring more power to bear on these kinds of non-trivial problems. For decades now, we've been programming single processor machines, and the single processor machines continue to get faster and larger and more capable, or at least it appears that that's the case to the untrained eye. But what I want to take a look at is what's really happening behind the scenes in terms of the increases of performance in computing in recent years. So we're going to take a look at some of the historical background behind this process and start out kind of with an overview of various performance characteristics of different processors over the years. So this table gives us some key metrics associated with different microprocessors over the years, going back to 1971, which was the year during which Intel released the 4004. This was a processor that many of you may have never heard of, but the 4004 gave rise to the 8008 and the 8080, and the 8080's successor, the 8086, is the processor from which we get the common abbreviation for processor architecture x86. So the 4004 is the great-great-grandfather of the 8086. So back in 1971, when Intel introduced this very first integrated circuit microprocessor core, these were some of the relevant characteristics. It had a quite slow clock speed by today's standards, 108 kilohertz, right? Not megahertz or gigahertz, but kilohertz. It consisted of 2,300 transistors. That's a very common metric that's used to gauge kind of the complexity of a chip. How many transistors have been laid down on the silicon surface to implement whatever functionality that chip does. And then the final column here, the feature size, basically is a measure of how small the transistors are. So 10 times 10 to the minus 6, it's 10 microns, basically. That would be the basic feature size, sort of the smallest component that the manufacturer at that point was able to etch onto the chip's surface. So that's where we started back in 1971. And if we inspect some of these metrics as we go, there's some trends that are pretty clear. First of all, in terms of processor cores, in the early going, we had just a single core processor on all of these devices. And we saw kind of an inflection point here around the turn of the century, where now we started seeing cores, multiple cores being placed on a single microprocessor. So 2 cores, 4 cores, 8 cores, and so forth. And that number has pretty much uniformly grown over the last 20 years or so. And that trend is widely expected to continue. In a similar way, if we look at the transistor count on each of these chips, we see that this number also continues to sort of grow. So we went from 2,300, we crossed the million transistor barrier with the 8486 around 1990, and we are currently into the hundreds of millions of transistors about 10 years ago. And then there's this kind of gap in the data. What's happened is that the processor manufacturers have been more tight-lipped about the number of transistors that they've been able to fit onto a chip, because that's competitive information that they'd rather not reveal. Another thing that we can see here in terms of the feature size is that we've gone from 10 times 10 to the minus 6 meters, or 10 microns, up to 14 nanometers, so a factor of 1,000 times smaller in terms of the basic size of components that we can lay down on the chips. And this is as of 2016, and in more recent years, we've seen that feature size shrink even further. So we can put more transistors on the same area of silicon, which allows us to have a more capable processor. Finally, let's take a look at the clock speed here. We can see that the clock speed started out around 100,000 ticks per second. Remember from ICS that the clock speed is basically a measure of how quickly the processor can run instructions. You could think of the clock as kind of an orchestral conductor, right? In order to keep all the musicians synchronized, the conductor provides a tempo for the music to be played at. And without that, the musicians would all go off in their own direction and you'd have chaos. In the same way, the clock on a processor is a signal that gets distributed around the entire processor chip, and it provides a way for all of the components on the chip surface to behave in a synchronized way, to collaborate together to execute instructions. So the clock speed has a lot to do with the amount of computing that can be done. The faster the clock, the more computing you can do in the same period of time. So the clock speeds came up rather dramatically by 1974. Intel was clocking the 8080 at 2 megahertz, and we could see that in around the turn of the century again, we reached the 1.5 gigahertz barrier, 1.5 times 10 to the ninth. But if you look at these numbers, what you'll see since then is that the clock speeds have gone up a little, but not by orders of magnitude, right? So here in the 2015-2016 era, we're talking about 2 or 3 gigahertz compared to just 1.5 gigahertz quite a while ago. So we haven't seen nearly the increase in clock speeds that we've had in the early going. And that has a significant impact on this question of whether or not we need to go toward parallelism or whether we can continue to expect increases in the basic clock speeds. Here's another visualization of some of these metrics. So this is the transistor count by year, and you can see that this is a logarithmic scale on the y-axis, as is the case for this and the next couple of graphs. So when we see essentially a linear increase on a logarithmic scale, that corresponds to an exponential increase in the number of transistors. And you can see here we sort of run out of gas at 2010 when the chip manufacturers stopped publishing information about this. Similarly, the feature size has continued to drop essentially at an exponential rate. to where we're getting now to the point where people are starting to wonder if we can actually make smaller and smaller transistors because the process of physically manufacturing them continues to become more and more difficult. But we're still basically following Moore's law, right? This notion that we're going to see dramatic increases in performance and dramatic decreases in size over time. Here's the rub. When we think about clock speed, so here we got 10 to the 5th up to 10 to the 9th, or 1 gigahertz here at the high end of this chart. Right around the year 2000, we saw that we got off of this exponential growth curve and it sort of flattened out. So for the last 20 years or so, we've been dealing with chips that are being clocked in the handful of gigahertz range, and the performance due to increased clock speed has not increased very much at all. The reason behind that, as you may recall from the ICS class, is something that we call the power wall. When we clock a chip at a faster and faster rate, the individual transistors, as they switch, generate some heat. So they're consuming power, and the result of their activity is that heat gets generated. And the heat has become the principal constraint to the increase in the clock speeds. The ability to carry that heat away from the chip has just become prohibitively difficult, to the point where the chip manufacturers have said, hey, we can't dissipate this heat any faster than we already can. And in order to avoid damaging the chips, we simply can't clock them any faster. So this power wall, this heat dissipation problem, has basically restricted the clock speeds in the small handful of gigahertz range. On the other hand, because we've seen feature sizes decrease and the number of transistors increase, we're still able to put more and more stuff on a chip. That's also the explanation for why the number of cores has continued to increase. So we can't clock them any faster, but we can put more functionality on a single chip surface. And the way that's been done both in CPUs and in GPUs in the last 10 or 15 years has been to increase the number of processor cores. So this chart shows the number of cores on these different processors over time. Finally, we've got a linear scale here on the y-axis, but we can see that at about the time that processor manufacturers realized that they were hitting the power wall after 2000, before 2010, they started to continue to increase the complexity of the chips, the number of transistors that they're putting down on the same piece of silicon. But in order to be able to give more processing capability at the same clock speed, the number of processors per chip increased rather dramatically. And this should kind of definitively answer for us the question of whether or not we need to be able to program parallel computers. Pretty much any chip you buy today is itself a parallel computer with anywhere between 2 and 24 and sometimes more cores on a CPU. And if you buy a GPU chip, the number of cores that are available to you is in the thousands on just a single chip. So again, the bottom line is that if we're going to write faster and faster programs, we aren't going to be aided or be able to rely on increasing clock speeds to make them go faster. We're going to have to be able to understand how to write programs that can be parallelized in order to run on these multiple core and many core processors. Let's take a look at sort of the extreme of the parallel computing world, and that's an area that's usually referred to as supercomputing. So what are we talking about when we talk about a supercomputer? Well, it's a kind of a moving target. A definition for supercomputer is, and I've said right here that it's intentionally vague, but basically a supercomputer is just what's the most powerful computer currently available on the planet. And so the definition of supercomputer has changed over time, but we kind of know them when we see them, right? They're the most powerful machines available. One of the important metrics that's used in determining the performance of a supercomputer is what's called a floating point operation. So you might think of this as a floating point multiplication or division. And the abbreviation for floating point operation is a FLOP. Kind of an unfortunate acronym, but there we have it. And then when we talk about flops, that we're now talking about how many of those flops we can compute per second. So flops refers to floating point operations per second. So usually we have some kind of a prefix because a single floating point operation per second isn't particularly interesting. So we now have megaflops and larger numbers of floating point operations per second. Here's a little table. So megaflop, gigaflop, teraflop, petaflop, exaflop, zettaflop, yottaflop. If we look at these in terms of their base 2 or base 10 exponents, you can see they're kind of the number of floating point operations per second. And these are the numbers that are currently being used, or the scale of numbers currently being used to talk about the performance of various supercomputers. An interesting place to go and look at this information is what's known as the top 500 list. So an organization keeps track of basically the fastest 500 known computers around the world and keeps statistics on their various performance. So you can kind of get a sense for where is the state of the art in very large-scale parallel computers by checking out the top 500 list. It's top500.org. I think this is actually linked. This slide is linked to that web page if you download this on the course website. Here's a picture of the number of cores on various of the top 500 machines over the years. So going back to the early 1990s, the number of cores on those machines was in the range of about 100 cores. And you can see here as of 2017 or 16, whatever this last value is here at the top, that these machines are now constructed of 10 to the 7th, right? That's 10 million processor cores, or in that general vicinity. So you can see that at the extreme, the very highest performing computers on the planet are parallel machines. It's not one processor that's super, super fast. It's a very large number of processors that are themselves quite performant in order to get these kinds of crazy performance numbers. So a single machine with up to 10 million processors. Pretty amazing. I mentioned the flops metric, right? The number of floating point operations per second. So this is a chart. Again, it's a logarithmic scale on the y-axis that shows the performance of various computers over the years on a particular benchmark of floating point calculations. It's called Rmax. It's basically the fastest that this computer can compute based on some standard benchmark programs. So what we can see here as of 2016 or so, the fastest supercomputer on the list was calculating in the 10 to the 5th teraflops range. So if I go back to this little table here, we can see that a teraflop is 10 to the 12th floating point operations per second. So at 10 to the 5th teraflops, that's the same thing as 10 to the 17th flops, which would be in the hundreds of petaflops range. So 10 to the 17th floating point operations in 1 second. To bring you more up to date with the latest and greatest, this is the #1 ranked supercomputer on that top500.org website as of November of last year. They've come out with rankings in November and June, I believe. So there'll be other rankings that should be coming out shortly. But Summit is a machine built by the Department of Energy. It lives at Oak Ridge National Laboratory in Tennessee. It uses IBM Power 9 processors and a whole boatload of NVIDIA GPUs. You can see here from the core numbers that there's 2.4 million cores in this one computer. And it achieves an Rmax of 148,000 teraflops per second. So it's extraordinarily fast. This other number here of R peak, that's kind of a theoretical maximum. It could peak out at 200 teraflops per second. But the sustained performance on that standardized benchmark is 148,000 teraflops. And you can see that the rankings as we go down the chart here are quite considerably smaller in terms of the number of teraflops per second that machine is capable of. It's also a pretty cool looking computer. Here's a photograph of the installation at Oak Ridge National Lab. You can see that this is just rack after rack after rack of Power 9 based servers chock full of NVIDIA GPU chips. So if the motivation for the course isn't sufficient already to be able to make use of a whole variety of different processor cores on any machine you can pretty much buy, even at like Best Buy or Newegg, a further motivation ought to be that when you're done with the course, you'll have a fairly good idea about how you could program a computer like this one.